loud enough. Okay. So first of all, I would like to thank the organizer, especially I would like to thank Nadia for inviting me. Personally, she took all the pains to make all the arrangements come from Dhaka to make my stay here. It was a wonderful stay. I brought my wife and daughters. They all had a wonderful time. Before leaving, they asked me to convey thanks to Nadia and also all my colleagues, former colleagues of the physics department. Do we have anybody from other department other than physics?
Yeah.
Okay, I know chemistry. Other students? All are from physics. Okay, that's great. So, the first slide is a kind of ad. It's a book only in December, 4th December, it's been published by CRC Press, Taylor and Francis. It's a book I have written with 3 of my Indian friends. I have changed the title a little bit. The title is Fractal and Enigma of Entropy in Percolation. Content will be the same, only the title is being changed. First, perhaps many of you don't know the word. Some of you may know the word. Forgive me if I am underestimating, but since I know that, I am the only person in Dhaka, in Bangladesh, who works in this area. Sometimes it is very painful. I don't have even one person to share my research. When I write an article, you need to share with friends and colleagues. When you submit an article, when you get the review report from the referee, you need to share. I do not have that opportunity here, so I'm assuming, at least for the students, I would like to make the talk as simple as possible so that all of you can work with me to understand Fractal. Yeah. You need the mic? Oh. Who is holding it for me then? Is it okay now? Okay. So, to understand Fractal, we have to understand what is not Fractal. If you want to appreciate Fractal, you have to first understand what is not Fractal. It involves us with Euclidean geometry that restrict ourselves, our boundary of our imagination to a line, to a square, to a rectangle, triangle, semicircle, circles, parallelogram, etc. Now, they have 2 common features. If I have a line, that's why I don't need. Do I really need that?
No, sir. No, sir. No, sir.
It's because I don't feel comfortable holding it and talk. So if I double the line, mass of the system is also doubled. If I triple the line length, size of the line, mass is also tripled. If I have a square, if the linear size is doubled, mass of the system is increased by 4 times. If I increase the linear size 3 times, mass is increased by 9 times. So, this is the relation by which mass and the linear size of the system is connected. It is called mass-length relation. The other property is density. How do we define density? It is the mass of the object and the volume of the space where the object is being embedded. So mass, as I said, from here, L to the power d, and the volume of the space where the object is being embedded is also L to the power d. So density is constant. What does that mean? So if I give you infinitely many points, indistinguishable points, or marbles, and then I ask you, decorate them in a line in order to constitute a line, or decorate them in a plane in order to constitute a space object which has dimension 2. What would you do? You would put them in such a way they are uniformly distributed so that density is constant. Doesn't matter the distance between 2 points, if it is this far or that far. If all the points are equidistant, if you put them like that, or if you put them very closely, they're the same as far as dimension is concerned. It will constitute a line or square lattice. Doesn't matter the lattice considered how far. Is that clear? To quantify further, so this is the visual effect. So statistically uniform. Okay? Still it is Euclidean object. Now, little bit of math. So if I have a length, I ask you to measure the size of the length that I have given you. What would you do? You will take an yardstick. I call this is delta. That means if I have a line, and then you measure 1, 2, 3, 4, so you get a number. And that number will depend on the size of the yardstick. Is that clear? Number that you obtain, the length by size of the yardstick, you get the number. Now, decrease the size by a factor of 2. The number will increase by a factor of 2 as well. If you decrease the size of the yardstick by a factor of 3, the number will increase by a factor of 3 as well. So if you decrease the delta by a factor of n, number will be n times more than you had earlier. If you do the square, you do the same thing. And the new number is connected with the old number by a factor of n square. If it were a cube, it would be n to the power 3. So I can generalize those 3 to 4 lines, putting into one equation is that. In the math class, you all know that a function is called homogeneous function if it satisfies this condition. If the x is increased or changed by a factor of lambda, then new function is connected to old by a factor of lambda to the power b. While a function satisfies this condition, the corresponding function is called homogeneous function. While if we know that for sure the function is homogeneous, there is only one solution of the function. It is power law. If you put back here, you will find that this solution will satisfy that. So it implies this is the homogeneous function. You can test with that. So the solution of that is this. It provides us with a processing procedure, how to define dimension. Now we have come to a very important point. When we were child, we were told an object has a dimension 1 if it has a length, dimension 2 if it has length and width, dimension 3 if it has length, width and breadth, right? And then when you came to college or first year university, you took a math course. There you were taught if the point of an object, to describe a point of an object, if you need 2 linearly independent axes, the object is 2-dimensional. If you need 3 linearly independent axes, the object is 3-dimensional. Did we ever question ourselves? Why are we jumping from 0 to 1, 1 to 2, and 2 and 3? Are there any objects which has dimension between 0 and 1, which has dimension between 1 and 2, or 2 and 3, if they are, how do they look like? So that is the point that we want to answer. Is that clear so far? If not, please let me know. Okay? So, there are many objects. In fact, we can only create Euclidean object artificially. So we have to create nature, create them. This is the cloud distribution, host of an ocean, thunderstorm, the nerve distribution in our retina, in our body nerve distribution, river basin. These are all objects which you cannot describe by Euclidean object. You cannot say what are their dimensions. So there are two things. One is object, its dimension, and the dimension of the space where the object is embedded. In this case, it is embedded, you can say that it's a two-dimension. But it doesn't have a dimension 2. It will have dimension between 1 and 2 for perhaps. Another thing is important here. If you take part of it, I took a picture of a part and I blow it up and I bring back to you. It will be hard for you to distinguish, to differentiate between this and my blown up picture. So part represents the whole in a statistical sense, of course. This also true for Euclidean object which has dimension 1, 2 or 3. But that is trivial. These are the objects statistically similar. Doesn't have dimension 1, 2 or 3. We'll soon see. So our goal is to understand and how to measure their dimension. So, if we take log on both sides, then what do we get? Log n equal to minus d log delta. And this is an equation of a straight line. So if I plot, so this is an object. I want to measure the dimension of that object. What I would do, I would put a grid, a square grid of length, say delta. And I will find the number of the boxes that contain these objects. And I record the number. And then I take another grid whose size of the squares are smaller. And this time again, I measure the number of the boxes or squares that contain this object. This time number will be higher. I make it even smaller. And then I take the delta, and the number. Take log on both, and I plot. This gives me a straight line. And the slope, as I say, slope will represent the dimension of the object. So if I measure this board with a square, you will always find the slope is 2. The log n versus log delta, the plot, the slope of that plot will always be a dimension. This is the most generalized definition of dimension of the object. Is that clear? So, object of such system which are highly ramified, stingy object. This is the when you see an object which is ramified and stingy, yet part of it similar to the whole, this is a potential candidate to be a fractal. Is it clear? Typically, dimension of fractal is non-integer, but it can have also integer dimension. So if the embedding space is 3-dimensional, and if the object has 2 dimensions, it is a fractal. So how do we define the fractal? So mass and length in this case, also like before, L to the power df but this time exponent is not an integer number. So if I measure the density now, density is no more a constant. So if you increase the length scale, density decreases. When you have density of points that you decorate, if the density depends on the length scale, you can be assured the object that you are measuring is a fractal. Is a fractal. Is it clear? So this is the visual view. What to expect when you are trying to see whether the object is fractal or not. So you have particles of all different sizes. This is one way. Now, question is, can we create artificially a fractal? The simplest example that you can think of is called, textbook example, is called Cantor's set. We'll see now. So, you start with a line of interval, say 1. It is called Cantor's set. You divide into 3 equal parts and take away the middle part. And surviving 2 parts, you continue to do the same thing as you did with this one. So you divide into 3 equal parts, take away the middle part. And take away the middle part. So in step 1, you have 2 intervals n equal to 2. Their sizes are 1/3 because I have divided into 3 equal parts. 1/3. So here you have 4 times 2 square. So in the nth step, I will have 2 to the power n number of intervals. And their sizes will be 1 by 3 to the power n. Then I take log on both, log here on both sides, eliminate n in favor of delta and plug it here. It's a matter of 2 steps, and you find n delta indeed exhibit power law with exponent non-integer log 2 by log 3. It is a fractal. So we can create object which doesn't have dimension, neither 1 nor 0. It is in between something. Is it clear, what I say? Fine. If not, please raise your hand. If you have questions, you can also ask me. One of the important things is that if you take x1, if you call it x1, x2, x3, x4, x1 to the power df, x2 to the power df, 3 and 4, if you sum them up, it's always equal to 1. And the bit that you cut and put in the bin, this bit, all the things that you have put in the bin, take them, add them together, you get equal to 1. So, there are plenty still left there. When George Cantor in 1750, he created this, he had no idea about fractal. Fractal was born only in 1975. Cantor died of depression because these then scientists, they did not like, because he created this, because a line is a set of points, infinite number of points. So he wanted to show that by cutting into pieces, what is left is still an infinite. So infinite actually is also, if any part is also infinite. They did not like this. In an open seminar, like today, Kronecker delta, you know, remember? Delta? Kronecker. That Kronecker, he openly protested and insulted him like anything. And he could not get out of that depression because he thought he was insulted in front of his daughter. So out of that depression he died. Anyway, only in 1975 this idea was brought back and found that it is indeed a fractal. Now, these points, if I redecorate them and put them uniformly and I walk along the line, I find that constitutes a line. But if I walk along this line, I find they are not uniformly distributed. So that is how you should understand what is fractal and what is not fractal Euclidean. Is that clear? So here rho is a constant. Here rho is not constant. So there are many other examples. This is also the fractal self-similarity. You blow this up, part, it will look the same as a whole. Here as well, if you blow this part, it will look the same as a whole. So these are all fractals, classical fractal. You can find any open any book, you will find those examples. Next, these are all constructed mathematically. Now, in 1995, while I was reading book on fractal, I asked myself, nature does not create fractal in that fashion the way I had discussed. Two ingredients are when missing. No object are being created blink of an eye. It takes time, it evolves. Nature loves also freedom to choose randomness. So randomness and the time, those are the two essence were truly missing from the examples that I was trying to explain. Is it clear? So I incorporated those two ingredients. So this is the equation that describes, to make it simpler, instead of breaking into three, this equation describes breaking into two pieces. And if I break two, how do I break? I break randomly into two pieces. Randomly. If I choose f equal to 1, and I keep that one of the piece with probability p, I take away with probability 1 minus p, and I continue that. So I don't want to go into details in math, I will just explain the essence of the problem. And then I see that again n delta is exhibit power with df now equal to the probability with which I keep the particle, that is the become the fractal dimension. So anyway, one of the ingredients hello still I have to explain. Despite I am breaking into three pieces randomly, it must exhibit also self-similarity. How do I exhibit self-similarity? So, to understand self-similarity, I will like 2 slides I will spend to explain what is called Buckingham pi theorem. So, if you want to do experiment, what do? You have first want to measure something. So observable quantity. That quantity may also depend on many other parameters. Like if you want to measure acceleration of an object, that may depend on force and the mass of the object. Similarly, if an object, it may depend on many other parameters. I have identified as many possible you can put it here. What do I do next? I classify them into 2 classes depending. So I say k number of parameters are linearly independent, dimensionally independent parameters. What does it mean? None of those independent parameters dimension can be expressed in terms of the power product of the dimension of the remaining parameters. For example, the dimension of this cannot be expressed in terms of the power product of the remaining parameters. So I say k number of them are independent parameters. ak plus 1 or ak plus 2 or an, all of them, their dimension can be expressed in terms of the k number of independent dimensions. Is that clear? So I have now 2 classes of parameters. So accordingly, so now ak plus 1, so since this can be expressed in terms of the power product of the dimension of this, so their product must have the same dimension as ak plus 1. So if the ratio will be a dimensionless quantity. Similarly, AK plus 2 divided by this, a dimensionless quantity. What does the dimensionless quantity mean? Can anybody answer this question? Numerical value of pi 1 remain invariant upon transition from one unit of measurement to another unit of measurement within the same class. Meaning, if I measure in centimeter, gram, this parameter, and if I change then in the meter, kilogram, still the numerical value of pi 1 will be the same. So, a quantity is called dimensionless quantity if the numerical value of that quantity remain invariant, doesn't change. Even if you go from one unit of measurement to another unit of measurement. Is it clear? So, by doing that, I can show the function f now is less number of variable I have to take care. I have n number of variable. Now I have n minus k number of variable. K is the number of independent variable. So it is already a huge simplification. How simplified is it? Let me explain. A simple example. A right triangle. Say I have 3 right triangles. And then hypotenuse, height and base I have A. What I do, I take the data. Say I put it here, C here. I measure the area as a function of B. I change the B, I measure the area. I change the B, I measure the area. So do I do also the same for this and same for that. And then I plot area as a function of B. For each of these, I have 3 lines. Now, when I measure area, I divide by c square, meaning that s is function of 3 equations are not coming, doesn't matter. So, s I measure in terms of c square. S by c square is what? Is a dimensionless quantity. B by c is what? Is a dimensionless quantity. The same data, I divided the area by the c square, so it's a dimensionless quantity. All 3 data collapse into one term. That means for a given value of b by c, for a given value of b by c, if b by c is a sine theta, if it is a sine theta, so for a given value of b by c, s by c square is the same regardless of its size. It means numerical value remain invariant because it is dimensionless quantity. This is exactly what our architect uses. You know, when you have to build a big aeroplane or big structure, you don't straight away work on a big structure. What you do, you work on a small model. Model is meaningless if you cannot connect the result of in the model to the prototype real system. Now, how do you connect them? The 2 real system and model, they are dimensional in terms of the numerical value of the dimensional quantity, they are different. But corresponding dimensionless quantities, they are same. When they are same, you make the connection. So, in physics too, when you see a complex problem, we make a model. And modeling is useless if you don't know how to connect with the real system. So, this part, despite its simplicity, simple, still the significance is far-reaching. What does it mean? When they collapse, it means that these 3 triangles are similar. This idea cannot say that we divided randomly. We will show that they are as well I will get data collapse. I will make the conclusion that it is similar. In a sense, cauliflower is a self-similar. How? This is a picture of cauliflower, or you all know about it. I took part of it. I dissected it. I took a picture. I blown it out, and I show it to you here. You say, oh, this is a cauliflower. Part represents the whole, of course, in a statistical sense. So, self-similarity, nature is always there in nature, somehow. So, there too, you see, I made a concentration of particles. Since I am breaking into two pieces, so I will have different particles. I measure number of particles per unit length. So, as the system is evolving with time, so I am keeping breaking, and at some point I found some particles. I plot Cx. And another time I took a snapshot, another data. So all these C, if I plot them in a directionless quantity, all three data collapses. Meaning what? These are evolving in time in such a way, each snapshot are similar, meaning self-similar. The same system is similar to its earlier, all the snapshots. So, in that sense, fractal is a self-similar, even though it is random. Is it clear? Okay. Next, we move to the network theory. I'll start with a few story. I will explain what is entropy, because entropy is the most enigmatic word. No one can say, I understand entropy. This is such a mysterious word. I will try today, at least we can pretend ourselves that we understand entropy, even though we don't. So, the story starts from in Leonard Euler. Have you heard any of you? Euler had a cataracts eye. So he got blind in one eye, and other eye also deteriorated. After a few years, he was completely blind. He became. Then he said one thing. Oh, thanks God. Now there is nothing to distract me. I can work undisturbed. And he proved his words. After he became totally blind, every week he published at least 1 or 2 articles. So, it is called Königsberg 7-bridge problem. Have you heard this word? 7 bridge. So, at that time, in Prussia, Königsberg was a very famous city because it is a port city, rich. So, mayor has built 7 bridges to connect 2 islands with the mainland. And people are trying to visit all the mainland, traveling, crossing each bridge once and only once. You cannot cross bridge twice. Is it possible? That was the question. So many people died, everybody failed. Then somebody told the mayor that there is one guy, Euler, who may, because mayor was very unhappy. Trial and error system, he did not like it. He wanted a proof, mathematical proof. So he invited Euler, he had to solve this problem. What he did, he considered 1, 2, 3, 4 as a nodes and bridge as a connection. So a network, at that time they call it graph. A network is a set of nodes connected by links, is a network. This graph theory remained in the domain of mathematics for 200 years. after 1736, 1959, for the first time, a paradigm shift took place. Because before then, Hamilton, Cayley, Cauchy, all those people worked on the graph theory. And only discrete math people, they knew only graph theory. It was not known by many, even within the math discipline. He was also a famous mathematician. He was called man of briefcase because he would always carry a briefcase, would knock to a scientist at a university, they say, I want to stay here for a few days and I want to work with you. So he would stay there, work few months, publish 2 or 3 articles, and one fine morning he would leave. So this way, he wrote 1,475 articles in his life with 493 co-authors. That's why if you Google it, you will find Erdos number. Erdos number 1 is called the people who has co-authored an article with him. Erdos number 2 is those who has co-authored with people who has random Erdos number 1 this way. So it's a Erdos network of authors. Have I made my point here? So he then asked the following question for the first time, that nodes network should be random. He asked how nature decides to establish a link between 2 nodes. This is a question for physicists, not for mathematicians. So he did not know the answer. But he took the simplest case. What is the simplest case? A set of nodes. These are dots are called nodes, indistinguishable. This node can represent our living cells, can be considered as a network of chemical molecules connected by chemical interaction. This can be individual connected by social ties, for example, friendship, Facebook. For example, co-authorship, right? Or this could be routers or computers connected by wireless or cable connection. This could be, each of them could be, it could be a power grid where each node can be power station connected by transmission lines. So, doesn't matter who are they belong. Erdos for the first time asked the following question. If I pick 2 nodes at random and I connect them, provided they are not already connected. Is the problem is clear? I have a disconnected nodes. Let me tell you one thing clear. Each node now, since they are not connected, can be regarded as a cluster of their own size, cluster 1. And the problem is, I pick randomly 2 nodes and I ask, are they already connected? If the answer is no, I connect them. If the answer is yes, I took another pair of nodes. And I ask the same question and I keep doing it. What is the tuning parameter? I observe the thing, various properties I will see. Here, this is a cluster of one color. So if I connect this, I will have 4, 7, and 2. I will have cluster of size 9. If I connect this link. And number of links that I have already added, a total number of nodes that I started. Their ratio is my control parameter. Is it clear? Now, what do I observe? Here is the order parameter. The largest cluster divided by network size, number of nodes that I started with. If I increase the T, it remains 0. And suddenly, it shoots up. It reminds me of what? There is a phase transition. It is reminiscent of phase transition that we are familiar. Whenever you have a problem, you have a tuning parameter, you see suddenly something shoots off, below this it is 0, above this it is non-zero. We say Eureka. we found something. It's a reminiscent of phase transition. Is it clear? Light, paramagnetic, magnetization is 0. Ferromagnetic. Like normal matter, superconductor. So many things it may be present. So what is the advantage of it? It is a simple model. Like architect use a model in the tabletop. Simple, without any quantum effect, without any many particle interaction effect. You get the phase transition here. Something at 0.5, it shoots off, non-zero. Is it clear? Here I have 3 different network sides. I've blown it up to this, and I see there is a crossing point. Just a passing node here. I'll come back to that point later. Now, one point is important. Whenever you see a transition, connectivity, emergence of large-scale connectivity is a theoretical underpinning or pinning of many seemingly disparate systems. The extent of connectivity that emerges at the threshold has a profound impact in the physical property of the system that we will see now. What is the transition? What happens? Below TC, largest cluster versus log n, I plotted. So if you increase the network size from 1 lakhs to 5 lakhs, largest cluster grows from 12 to 25 below TC. Above TC, if you increase by the same number, it increases largest cluster of this side, 50,000 to 250,000. So huge. So minuscule size to a giant cluster. So as you increase the time, t, you see that suddenly above TC, an emergence of giant cluster, almost all the nodes are connected, few are disconnected. If you increase further, they all get connected. So that we'll see there are other important things as well, like entropy, specificity, susceptibility. We can define everything there. Is that clear, sir? Are you following? So I want to make this point clear that there is a phase transition. Below TC is one thing. Next problem is I do little bit of change I make. Instead of picking one link previously, I pick 2 links, 2 pairs of nodes. Ultimately, I will also always add only one and discard the other one. I want to see what is the impact of choosing 2 instead of 1, but ultimately, even if I add only one, with a precondition, the one that I add has to satisfy a test of precondition. What is that? If I add this link, it makes a cluster of this, and then it joins 2 clusters. So each link addition, which connects the 2 nodes, each node will belong to a cluster. So this node belongs to a cluster of size 7, this node belongs to a cluster of size 2. I take product of these 2, 14, and I take product of these 2, 16. So in this case, pi 1, product of these 2, is smaller than pi 2. So I say, I will add this one, I will discard this, put back in the jute basket. I will pick in the future. Is that clear? Or I can do another thing. I can add these 2 clusters, and if sum is smaller, I will keep the one that is small, sum is smaller, and I will discard if it is bigger. Is that clear? What am I doing? I am encouraging smaller cluster to grow faster. A bigger cluster, I am suppressing. I am discouraging them to grow fast. Important point. What is the impact? What is the impact? Look at this. So one obvious impact, the transition will be delayed. Okay? Before 0.5 transition, now 0.88. It's obvious because I'm encouraging smaller to grow faster. So it is can be taken for granted. It will be. But when it happens, with one addition of one or two links, bang! You see a largest cluster grow up like anything. Before it was slow growth. People who proposed this model for the first time, it appeared in Science in 2009, one of the top journal, Science and Nature Equal Footing. So they thought that there is a jump. Since I regard that as an order parameter, and in the discontinuity in the order parameter means it is a first order phase transition, like liquid to ice. But it was a mistake. So many scientists, they jumped onto the problem, and then many articles published. Finally, solution is found that it is actually second order phase transition. It is not a jump, it is a continuous. And if I plot this for different network size, I see it like this. So as the network size increases, all 4 or 5 plots, they process at one point. What is that point means? If I could write a polynomial equation as a function of t, they all meet at one point, means that is the root of the polynomial simultaneous solution equation. That means that is the TC value, exact TC value. And as I increase the network, I see that it's shifting towards that. That means in the network size infinite, I will have a step function act like this. So below TC, it would have been 0, above TC, this is 1. So it is a perfect demonstration of a phase transition. Is it clear? Order parameters. Now, here again you see the below TC minuscule size, above TC giant cluster. But this time, when the network is at 500, giant cluster is almost contain 400 nodes, which is giant, really big cluster. Now, important, it is connected with the percolation theory. So, if I have a grid, initially each white ones are insulator. These white ones are insulators. So, if I put a battery and something to measure current or an emitter or a bulb, when the current passes, it will blow. Then, when everything is white, there will be no current. And then I randomly pick one of the white and replace it with a metal. And I continue doing that, current will be still 0. Suddenly at some point, there will be path spanning from one end to the other end, and you will see for the first time, your light turned on. Meaning, there is a path for the first time that span from one end to the so current will flow. So, this is called percolation, like word comes from coffee percolator. So, what is the value? The total, if the PC is 59.27% of the sites are occupied, it is guaranteed you will have a spanning cluster for the first time. And then current will go on and on and on. Exactly the same. So, if I plot 0.5927, they process, which is the same as this. Of course, in the case of network, you will not have a surface. You don't have an edge. So you cannot define a spanning cluster that spans from one end. There is no end to the other end, opposite end. So, analogous to that spanning cluster, we have largest cluster. Say. Now, what if we encourage the larger cluster to grow faster? We see that TC happens, smaller value TC, not delayed, earlier takes place, but even slower. So it's very counterintuitive that you are encouraging smaller cluster to grow faster. It is delayed, so everybody has a lesson to learn here. It can be, you see, node can be individual and link can be disease, viral spreading, so or opinion spreading or information spreading, right? So if you try to intervene to delay the spreading, yes, it will be delayed, but there is a danger. When it happens with a bang. It can create problems. So everybody should be aware of that. So one thing is that, so what are parameters if you compare? This is the inverted explosive percolation, this is random percolation, and this is real explosive percolation. That where you pick a smaller cluster to grow faster if you encourage that. But if you want to talk about phase transition, phase transition is classified whether it is first order or second order depending on the entropy. Entropy is important. 1959, the idea of percolation was proposed. It took more than 60 years. People could not define how to define entropy. Some people in 1999 tried, but it was wrong actually. I proved wrong. And then in 2017, with few of my students, master's thesis students, we defined entropy for the first time. We had a long fight with the referee, but finally we won the battle. But before I explain what is entropy, I would like to start with a story, if you bear with me. One Western guy, scientist, went to China to work with a Chinese friend in a lab. During the daytime, he worked in the office, he went to lunch with his friend, so no problem. But this guy, Western guy, did not know any Chinese. In the evening when he went to the dorm, he had to go out for eating out to a restaurant. So he was looking for a restaurant, he found a restaurant. So, and price was suitable within the rent that he wanted to spend. He went to the restaurant, he sat in a table, waiter brought the menu, then he saw. He could not read anything, but prices were written in English. So that is usually do, the price is important. So then he pointed finger at random, bring this, bring that. Waiter brought food, he was happy. He came next day, and the day after, and the day after. After a few days, he found another restaurant in the same neighborhood with a similar price range, similar standard. He thought, oh, why not there? So he talked to his friend, said, I prefer the other restaurant. His friend knew how he placed his order. He placed randomly. So why are you choosing that one instead of this? Because they have more options. The menu list, there is 1,000, and the one I go, they have only 500. How does that matter? You eat, at a time, you eat only one dish, and that too you choose at random. He said, I prefer options. In fact, that is what thermodynamic system without brain. You might be thinking that man is foolish. All the thermodynamic system, atomic scale, all the atoms, they do exactly that. They prefer options. And that is the entropy. We'll talk about this now. You understand the story? It will be clear soon. Now, for percolation or our problem, I define the Shannon entropy. So, cluster size and number of nodes I define as mu I. This is the definition of Shannon entropy. So, initially at time t equal to 0, all the nodes were isolated, and their cluster size is 1. So 1 by n for all of them. So all of them are 1 by n. And there if you put, you will get the maximum entropy. Meaning, if you pick one of the nodes, they are all labeled, color, say blue, black, whatever color they have, all different colors. So seemingly it is disorder. And if you pick one at randomly, somebody asks, what is the probability that is blue? Probability is 1 by n. It's highly confusing, highly uncertain. When all the nodes are connected, they have one color. Which cluster do they belong? You say with certainty, there is only one. Entropy is 0 here. So there is a transition from maximum entropy to a minimum entropy. And in between what happens, we'll see it soon. Now, how is it Shannon entropy is connected with the Boltzmann entropy? Do you know the Boltzmann? He had also trouble. In his tombstone, this formula is written. Because he was giving for the first time atomic structure. At that time it was statistical physics were developing. So for that, he was not accepted by the contemporary scientists. So he had depression, he committed suicide, he went to Vienna with his daughter, and he committed suicide there. But anyway, what is the omega? Omega is called the multiplicity. So if you have n number of nodes, and if you have n number of clusters, and their sizes are these, how many ways you can have them? How many ways there are arrangement? This is the number of ways you can arrange. Because if S1 cluster, all of them is the same color, if you arrange themselves, it will not contribute to a new arrangement. So this is omega. So if you put it here, and then take log, use the Stirling approximation, you find that log omega equal to n times, which is the Shannon entropy. So Shannon entropy actually, Boltzmann entropy per site equal to n by the n. Say we put k equal to 1. So basically, so Shannon entropy and Boltzmann entropy, there is no problem here. Next, this is the Boltzmann. Now, if I plot entropy, we see that in the case of random, one link will pick at random, which they do not start at one point. Here, explosive percolation, we see that they meet at one point, and the network size increases, entropy increases too. And if I plot all these three, inverted explosive, random, and explosive, entropy is highest there. Higher means what? Now, if I pick one, the two link, I encourage a smaller cluster to grow faster. How can we interpret in terms of entropy now? Decreasing entropy is more favorable or increasing entropy is more favorable? If you encourage a bigger cluster, you decrease entropy by a larger amount, which is not favorable, it is costly. Cheaper, in terms of energy, cheaper if you preserve higher entropy. Our instinct is to go disorder. Bangladesh is more disorder because we move by this instinct. To keep order, you have to put energy, brain, you need brain, cost. So, now, entropy and order parameter, when you plot them together, it's important very much. Order parameter, why do we call it order parameter? Because when magnetization is non-zero, system is ordered. Meaning there is a net magnetization. When system is ordered, their disorder is minimum. When order parameter is 0, system is disordered. When order parameter is maximum, system is disordered. Entropy is minimum. So they are opposite. And when they cross together, we know that paramagnetic to ferromagnetic transition is accompanied by symmetry breaking. We can see here there is a symmetry breaking, disorder to order. Suddenly they change. So you can classify this is a disordered phase because high entropy, zero order parameter. This is an ordered phase. High order parameter, zero, almost zero entropy. So percolation 2, like reminiscent of paramagnetic to ferromagnetic, it is also accompanied by symmetry breaking in some sense. But in the case of random percolation, it is not. I am writing an article right now. I am claiming that these two actually infinite order phase transition. This is not an order disorder transition. Like a post-established the Nobel Prize got last year, like that system. In the case of percolation, the square lattice 0.59, this is also an order disorder transition. So explosive, when you encourage the smaller cluster to grow faster, this is better as a percolation, but these two are not. Now, going back to what is entropy. So if I give you 5 coins, and you toss them, how many ways you can have 5 heads? There is only one way. How many ways you can have 3 heads and 2 tails? There are 10 different ways. And 2 heads and 3 tails, each of these are equally likely. But if you do, then within Western scientists went to restaurant, he said, I love options. More options, more freedom. And system try to stay here. Higher entropy is those who studied both Einstein statistics. We calculate T, W. Do you remember? Multiplicity W. And then what do we do? We maximize it. Because most likely state is the one where the probability of options is maximum. If I increase, instead of 5 coins, if I have 100 coins, then I see 50, there are there are 10 to the power 28 number of possibility, while there is only one possibility, W. So this is the most likely. Many options. Most of the time you do, you will find this. This is the highest entropy. So that's why we do that. Another example, if you have a beaker, if you concentrate a color, what happens? They spray it. Did we ever see color, spreaded color go and back to the concentrated point? It never happens because of entropy. If we break a wine glass, it shatters. Did you ever see all the shatters pieces joined together become a wine glass? Microscopic level, reverse process, physics-wise, there is no problem. Because when you break a glass, what do? You increase the entropy. You also heard the second law of thermodynamics. Entropy always increases. So in a macroscopic point, that increasing entropy means that is the time error. Microscopic level is two-way street. But when it emergent behavior, it only increases entropy. There is only one street. So here I put 6 sheets, for example, concentrated. And this farmland. Each farmland has 3 partitions, small farmland, owned by 3 different people. And I set them free, and they can go anywhere. And I open the gate here. And I have a snapshot. I keep on taking pictures. After some time, you will find most likely is that 3 ships are here and 3 ships there. How many ways you can arrange? You see that there are 29, 28 different ways. There are 100 ways here, if you increase the number of sheets, you get a delta function. So in a thermodynamics, you have millions and millions of sheets. You will find they are scattered. That's why when you put them concentrated point, they spray, because that is the natural direction where the entropy increases. That is the second law of thermodynamics. Is it clear? So even both science and statistics, what do? We have E1, E2, E3, E4. So these are the energy levels. And G1, G2, is the energy states. The question is, assume that n number of particles in the G1 state we're having E1 energy. How many ways you can distribute? So what you want to find? Non-multiplicity. They can be arranged. Here G minus 1 means what? Here 2. Here 2, you see, I have 3 partitions. I have taken 2 because particle cannot be here. To make it inside, I have to, if there are 3 partitions, I will take 2 particles. As a partition, 2 partitions and 6 particles, how many ways they can arrange? Similarly, G, so I have, say for example, I have 1, 2, 3, 4, 5. 5 energy level. I cannot, this many particles I cannot put here. I cannot put there either. What I have to do, I have to put here, inside the energy state to ensure that if there are 5 energy states, I have to consider 4 of them. So, Ni number of particles, Gi minus 1 number of partitions can be arranged themselves in this many ways. And then we maximize this. This is the most probable state. As I say, more options, most probable state. Other states are probable because this is like so much delta function. You have so many particles. Small particles you can find sometimes there and there. But many particles you will only find one state. This is the statistical mechanism. Many particles, the game of the many particles. Emergent behavior is due to the many particles. Important here. That's why you get the delta function, and that's why you have to maximize the W, multiplicity. So we maximize this, and then we get the number. Here too, the free energy, since we know that entropy now for percolation, so what happens? Equilibrium state is what? Equilibrium state is 1. In the disorder state, system in the minimum free energy, how? By in the disorder phase, by maximizing the entropy. In the ordered phase, system in the minimum energy state, by minimizing this. So there is a competing effect. So here I am in the disordered phase. I give the maximum entropy. That's why this is the state which is energetically more favorable instead of this and that. That's why this is not the one that is permissible in terms of entropy. Now, once I have defined entropy, now if I claim that my problem can describe phase condition paramagnetic to ferromagnetic, for example, as a prototype example, I have to define also susceptibility. I have to define specific heat. Order parameter I already defined. Susceptibility is the one. If I know the order parameter, I know the magnetization. If I take the derivative with respect to external magnetic field, I get a susceptibility. Similarly, if I differentiate order parameter with respect to T, I get susceptibility. Now, as I increase the network size, the peak increases. I take the network peak size as a function of network size. I plot the log scale. I find that power law. So, slope will give me the gamma by mu value. So, I then, each value of the peak data, I divide by this value. and then I plot it again. So chi times n to the power minus gamma, so I divided it by, and again I plot the same data. I measure, so this divided by this is a what? Is a dimensionless quantity. And hence, all the peaks collapse into one point. Now, I measure the width, t minus tc. And then again plot log t minus tc versus log n. I find slope, and I say that they go like this. So, if I divide by this is again a dimensionless quantity. I plot this and this versus that times n to the power minus 1 by gamma. Sorry. 1 by gamma. All the distinct data collapse into one universal curve, both for product terms and this one. So from that way, I can find that susceptibility diverges with an exponent gamma in the same fashion. Susceptibility law, susceptibility diverges at a critical point. So similarly, I define and specifically I found the same thing. Order parameter also. I'm just going into different. There is no point of discussing. Now I want to talk about network. So at TC, the largest cluster. Now I want to measure the degree distribution. What fraction of this largest cluster, which is now network, what fraction of the nodes has a connectivity, say k value. If I plot, then it's a Poissonian distribution. So that means this average value can represent my network. Average value can represent network. In 1999, for the first time, a paradigm took place. Paradigm shift. Barabasi and Albert, they wrote a robot program and sent it to the internet, collected the data of www and internet network, and then they plotted the same thing. They found that degree distribution is not a Poissonian. Now it is the power law. What means that there is a network, there are networks where there are hubs, where huge number of connectivity. Most of the nodes are poorly connected. Some, very few of them are hugely connected. There are many networks are like that. That is important. Why is it so important? Most of the natural network, like our brain. Listen to me. Our brain is also a network. Neurons are nodes. They are connected by axons. What if all the neurons had the same number of connectivity? That means every neuron is connected to, say, 100 other neurons. What kind of brain would you have? Stupid brain. Most stupid brain. Here, if a mosquito bitten here, message to go to your brain, asking instruction to the hand to kill. By the time the mosquito will suck all your blood and he will die there. What kind of brain is expected? Your brain must have some neurons which are hugely connected. It makes the geodesic path length between any two nodes smaller. So that's one of the important network. So this network, peak around network, is not good one. This is called scale-free network, where you have power or degree distribution, exhibit like a PK, like this, only a few. So if you plot log and log of them, you find a straight line, you find a fat tail as well. This fat tail has a significance here. It means that there are nodes in the tail which are scarcely distributed, not uniformly closely, scarcely spaced. When you plot in log scale, you find a noise. So that kind of network, WW network, internet network, brain network, power station network, co-authorship network, many networks have this property. This was published in 1999 in Science. In the same year, there was another article published which is called Small World. But before going to Small World, let me tell you, Baravasi, so they wanted to explain, to make a model that could give you a power law distribution. What can they do? So they realized for the first time that what is the problem with the error sign network? That was the problem that number of nodes are static. So they realized this fall. Then they prescribed a model that nodes, real network must grow with time. When new nodes come, they were looking forward. How do they decide which one to connect? When new node joins the existing network, which one to connect? They said, real network, so new nodes prefer establishing links with the highly connected existing network nodes. That means reach-get-recharge phenomena is important. So growth and this preferential attachment, when you put them together, you get this. So this is the preferential attachment. You solve this equation, you find exactly power law. So here, like our www is not a static. You are uploading new web page every day. New computers, routers are adding to this internet network. Brain's connectivity is not static as well. So this is one of the important ingredients. And then you can solve the equation and you really see that it exhibits power law. So these are the one that shows that there are some halves. So size of the circle represents the number of connection they have with other nodes. This is the internet network. Okay. I also proposed one network which was published in 2017. I will just try to skip those. Now, small world is important. This was published in Nature. In order, so for example, Currently Fregis, of a Hungarian scientist, literature, writer, he wrote a book many years ago. He conceived the idea for the first time that two persons in the universe, if you pick randomly, you can connect them on average 6 number of acquaintances. So what does it mean? You pick a person in the village, a woman, and President Obama, for example. How many acquaintances do you need to connect them? So that woman perhaps has borrowed money from a Grameen bank in the village. So that lady knows the manager of that bank. Manager knows district manager, and he knows Professor Yunus. Yunus knows Professor Obama. In fact, some half can reduce the distance between nodes. That is the real message that I want to convey. Another important parameter is called clustering coefficient. So this is clustering coefficient. I want to measure the clustering coefficient of this node. This it is connected to 4 other nodes. I want to know what is the clustering coefficient of this node. So how many ways these 4 nodes could be connected? How many links do you need? 4C2 number, 12 links. How many links they have? 0. How many links they have? 1, 2. How many they have? 1, 2. How many is necessary to make them completely connected? 12. So how many of them? Okay, here are this all covered. So this is connected with that is connected with this is connected with that is connected with that, and this is also connected. So 6, so 1, 2, 3, 4, 5, 6 of them connected. So it's connection between 1. Here 2 by 6 1/3. So when everybody is connected to everybody else, the clustering coefficient is 1. If none of them is connected, clustering coefficient. So you measure each node clustering coefficient, you add them together, and you divide by the network size, you get the mean clustering coefficient. So these two parameters can represent whether the network is small one, like currently say, 2 persons can be connected, remotely chosen, randomly chosen, can be connected by 6 number of acquaintances. So to demonstrate that, so you have a regular network. So what do? You just rewire them. You pick one of them randomly, you reconnect them. You see? So by small change rewiring, suddenly let distance between them reduced by a huge number, but clustering coefficient is still high. That represents the small world network. Okay? Now they are saying that time is over. I also feel almost. This summary. I leave it for you to read. And I don't want to waste your time anymore. And thank you very much for your patient hearing. I appreciate it very much.
এটা সামারাইজ করবেন
কোনটা?
এটা একটা আপনি বুঝতে বলেন
নেটওয়ার্কটা? What we have learned, what is strictly self-similar and statistically self-similar, the data collapse we used. We first solved the model analytically and found that the fractal dimension of stochastic fractal. And random fractal dimension is always smaller than the strictly self-similar fractal. That is one thing. We proposed exact algorithm to solve numerically and found that numerical result perfectly matches with our analytical solution. We show that fractal which emerges through evolution in time exhibit dynamic scaling. That's why they are self-similar different snapshots. Dynamic scaling different snapshots similar means it's a symmetry. And we also saw that there is a conservation law. We know that Noether's theorem. Whenever you have a conservation law, there must be some symmetry behind. And in this case, symmetry means self-similarity. We have shown that Shannon entropy for percolation is the exact equivalent counterpart of entropy of thermal phase. We show that like its thermal counterpart, percolation too is an order-disorder transition. And hence, it too is accompanied by symmetry breaking. Percolation on address-varying network is not an order-disorder transition. We have defined specific heat susceptibility for percolation and have shown that it diverges at the critical point exactly in the same fashion as it does in the thermal counterpart. We have shown that loose group inequality, I have mentioned this. Part of graph theory and work on the time axis to appreciate how it evolves with time. Paradigm shift, we have discussed air-friendly network, and finally small world and parallel network, we have discussed why the scale-free networks are found.